In this lesson, we're going to determine the optimum mixed strategy for a player if a playoff matrix for a game is either a 2 by n or an n by 2, or can be reduced to such using dominance. So we're going to start off with an example from last lesson. This is an exam style question. You might want to pause the slide here and have a go at the question first. So question A asks us to explain why Dan should only choose to play two of the three strategies, and question B asks us the same for Christine. So the answer would be that strategy 1 dominates strategy 2. This is for Dan. We've given the reasons why. So we said because 1 is greater than -1, 4 is greater than or equal to 0, -2 is greater than or equal to -2. So that is the reason for why Dan should never play strategy 2. Make sure you give this as part of your explanation. And then for B, we can see that for Christine, strategy 3 dominates strategy 1. Again, giving reasons. -2 is less than or equal to 1. Remember that small numbers are better for the person who's on columns. -2 is less than or equal to -1. 0 is less than or equal to 1. So we've given the reasons. So therefore that tells us that Christine should never play strategy 1. So the next part of the question, part C, we're going to find an optimum mixed strategy for Christine. So the question set out below shows how you should set up the solution. So you would start by saying, let Christine play strategy 2 with probability of Q. You can use P if you like here. Strategy 3 with probability 1 minus Q. Notice that we have removed the row and the column of the strategies that were dominated previously. So we've reduced it to a 2 by 2. So we then need to state that under each of Dan's choices, the expected losses for Christine, remember that these values are what Christine can expect to lose each time, are. So under Dan's option I, or 1, we're doing 4 times Q, so 4 multiplied by the probability, -2 times 1 minus Q. That's -2 there times 1 minus Q. Simplifying this down gives us V equals 6Q minus 2. We're then going to say that for Dan's choice 3, Christine's expected loss is -1 times Q and then 0 times 1 minus Q, which leads us to V equals -Q. The next step is to solve this. So because these are both V equals, we're going to set them equal to each other. We end up with Q equals 2/7. V is therefore -2/7. We now need to put these two numbers back into the context of the question. So we then say Christine should play option 2 with a probability of 2/7. That's Q. Option 3 with a probability of 5/7. That's the 1 minus Q. You also need to say that she should never play option 1. You would then say that her expected gain is 2/7. Remember that a value of -2/7 means that Dan is losing 2/7, so Christine is winning 2/7. This is because V is -2/7. So we're now going to consider this game. You can see that each player has 3 options to begin with. However, we can use dominance arguments to reduce this slightly. So we can see that Rose would never play strategy 3. That is because strategy 1 dominates strategy 3 for Rose. Remember that you'd explain why this is. You would say because 3 is greater than or equal to 2, 1 is greater than or equal to -1, and -1 is greater than or equal to -2. So we can reduce this, but we still have a 2 by 3 matrix. If a payoff matrix can be reduced to either a 2 by n, so 2 rows and then any number of columns, in this situation we've got 2 by 3, then a mixed strategy can be found. We're going to need to graph the expected payoffs for player A under each of these choices. If we had a situation where the matrix was an n by 2, so n rows and 2 columns, then we could still use this same strategy, but we would need to transpose the matrix. So we'd need to interchange the rows with the columns. We'd also need to multiply all of the elements by -1 because that would then give us a payoff matrix for player B instead of player A, or in this case C instead of R. And we would have changed it into a 2 by n by doing this transpose. So the method for a 2 by n starts off very similarly to the method for a 2 by 2. We start by assigning probabilities for the player on the left-hand side to play each of the strategies. So we're going to have player R in this case playing strategy 1 with probability P and strategy 2 with probability 1 minus P. So there always needs to be just 2 rows in this situation so that we can assign the 2 probabilities. However, we can have as many columns as we like. So the next thing is to then calculate what the expected payoffs would be for each of Colin's choices. So if Colin were to play strategy 1, then the expected payoff for rows would be 3 times P minus 3 times 1 minus P. So we get the equation 6P minus 3 equals V. We're then going to do the same for Colin's strategy 2. So here we've got 1 times P and minus 1. That's 1 minus P again, that equals V, leading us to 2P minus 1 equals V. We've then got Colin's third choice, strategy 3, and the expected payoff here for rows is minus 1 times P and 4 times 1 minus P. So we end up with 4 minus 5P equals V. Now, because we've got 3 equations here, we don't know which of these to use. So we're actually going to draw a graph. We are going to have 3 equations here. We're going to plot a graph with the probability going along the horizontal axis and the value, so the expected gain, in this case for rows, on the vertical axis. So probability can only go from 0 to 1. So the horizontal axis will start at 0 and end at 1. However, because the value of the game can either be positive or negative, depending on whether rows is gaining or losing, we can then have positive or negative values on the vertical axis. So what we're going to do is we're going to plot each of these 3 graphs as straight lines. Because they are straight lines, we only actually need to find 2 points on each line. So we're going to choose the 2 easiest points, which are P equals 0 and P equals 1. And for each of the 3 lines, we're going to substitute in P equals 0, P equals 1, join together the 2 points, and that will give us a line. Now we need to be as accurate as possible here because we need to know which of the 2 lines are going to be used in the final calculation. So, starting with the first equation, so we're going to start with 6P minus 3 equals V. So we're going to be plotting this on here, remembering that V is going to be the vertical axis. When P is equal to 0 here, V equals minus 3. So that tells us that 0 minus 3 will be a point on that first line. When P is equal to 1 in this equation, then we end up with 6 times 1, take away 3, so V is equal to 3. So the point 1, 3 is also going to be a point on here. We'll also just do the same for the other 2 lines while we're calculating. So for the second line, when P is equal to 0, V is equal to minus 1. And when P is equal to 1, V is equal to 1. And for the third line here, when P is equal to 0, we get V equals 4. And when P is equal to 1, V is equal to negative 1. So those 6 points are going to be plotted to give us these 3 lines as straight lines. So we notice that the smallest value of V we've got in any of these 6 points is minus 3. So we're going to draw our vertical axis starting at negative 3. And we notice the highest value of V we've got is 4. So we're going to go up as high as 4. So that's why we've held off drawing the vertical axis so far, so that we know what scale to use sensibly. So we can now put a vertical axis in, going from V equals minus 3 up to V equals 4. Try to make these as evenly spaced as possible so that the lines are as accurate as we can. And we're going to plot each of those points. So the first line goes from p equals 0, v equals -3. So the point 0, -3 is here. The other end we've got when p equals 1, v equals 3. So 1, 3 is a point. Joining those together will give us this straight line here. So for the second line, we're going to plot p equals 0, v equals -1, and p equals 1, v equals 1. That gives us this line here. And for the third line, we're going to plot p equals 0, v equals 4, and p equals 1, v equals -1. So the third line we get is here. Now it's a very sensible idea to label each of the 3 lines so that you know which one you are working with here. So we now need to consider where on this graph will give the optimum strategy for Rose. In other words, minimising her choice of loss. Now, as P varies, depending on which of the 3 choices Colin makes, this changes Rose's potential outcomes. So, for example, for quite a small probability down here, Rose has the chance to win quite a lot if Colin chooses option 1, but also has a chance to lose quite a lot if Colin chooses options 2 or 3. So as the probability moves along, you can see that these change, and by the time we get to the other end, Rose's outcomes are quite different. So values that were previously quite low are now quite high, and values that were quite high are now quite low. So ideally, we need to find a point somewhere in the middle where none of the values are too bad. So we're basically trying to find the points here that is still underneath all 3, or at least on all 3 of the lines, but as high as possible. So in other words, how high can you get underneath all 3 lines? So we're going to demonstrate how it's actually going to end up being this point here. So this is the feasible region. We call this the region, it's underneath all 3 of the lines. We're looking for the highest point because we're saying the worst case scenario is still quite good. So regardless of which of the 3 lines get chosen, the worst case is this point here. It's the highest point that is still under all 3 of the graphs. So we can see it's highlighted there. How would we find that point? Well, we need to decide which of the 2 lines it is that gives us that point. And the 2 lines that give us that point are 4 minus 5p, this line here, and 2p minus 1 here. So it's those 2 lines, when they intersect, that is the optimum point. So in other words, the third line is not involved at all. So this line here, 6p minus 3 equals v, that line is not used because that is not part of this point of intersection here. So we're going to intersect the 2 that are included. We end up with a value of p equals 5 over 7 and v equals 3 over 7. The line that was not used at all, the 6p minus 3 equals v, that option will not be played at all by Christine. So this tells us that over 7 games, in order to minimise her risk of loss, Rose should play strategy 1 5 times and strategy 2 twice out of 7 games. Or another way of saying that is that she should play strategy 1 5/7 of the time, or probability 5/7, strategy 2 2/7 of the time, or probability 2/7. And if she does this, she can expect to average a win of about 3/7 every game. Now for each of these 2 games, find the mixed strategy for player A and the value of the game. So you will first of all need to reduce the matrices wherever possible using dominance, and then find the strategy for player A. So first of all, we can see that player A will never play option 2. That is because it is dominated. It's always dominated by option 3 because the values in option 3 are all larger than the corresponding values in option 2. So we can reduce the matrix. Now the values we should have ended up with here, if we had assigned probabilities P and 1 minus P for player A, are these three values here. This is the graph we should have ended up with by plotting each of the three lines, the expected outcomes, and we can see that the highest point underneath the three lines is there. So we're going to be intersecting P equals V and 4 minus 7P equals V. This gives us a value of P as a half and V as a half. So to put that into context, what that is saying is that player A will play each of the two strategies with probability a half, and if they do that, they can expect to win approximately half a point each time. For the second game, we can see that strategy A is always dominated. So it's dominated by strategy 3. So player A will never play option 1. So therefore, they will play option 2 with probability P and 1 minus P. These are the three values you will get. Plotting these, you will see that the highest point underneath all three lines will be at 2P minus 3 equals V, intersecting with 2 minus 4P equals V, so it's here. So to intersect those 2 points, so A will play strategy 2 with probability 5/6, strategy 3 with probability 1/6. They will never play strategy 1, and they can expect to lose approximately 4/3 every time. So we're now going to go back and work out a mixed strategy for rows. So we previously looked at this example here for Rose and Colin. We're now going to calculate the same strategy but for Colin instead. We already did this for Rose. Now we had that the probability for Rose were 5/7 for option 1 and 2/7 for option 2. We also know the value of the game is 3/7. In other words, Rose can expect to win 3/7 each time. We can now use this to help find a mixed strategy for Colin. Now there are two ways of doing this. The first way is actually to go back to the graph that we showed initially, and the line that was not used in the intersection. Remember, I mentioned that Colin would never play that option. So one strategy is actually to eliminate the line that was not used and say Colin will never play that strategy, and repeat the process now with the other two to find the mixed strategy for the other two options for Colin. A second way is not to use the graph that was previously drawn, and instead to assign two probabilities. So Colin will play option 1 with probability P, option 2 with probability Q, and then because all three probabilities need to add up to 1, option 3 with probability 1 minus P minus Q. We're then going to calculate each of the expected outcomes. So if Rose plays strategy 1, then the expected outcome, so the gains for Rose or the losses for Colin, are 3 times P, and then 1 times Q, and minus 1 times 1 minus P minus Q. So you can see we've actually got more variables here. We end up with 4P plus 2Q minus 1 equals 3/7, or 2P plus Q equals 5/7. If we then do the same for Rose playing strategy 2, we get an expected outcome of minus 3 times P, minus 1 times Q, and then 4 times 1 minus P minus Q. Simplifying down to this here. Now we've actually been able to put in the value of v that we found earlier because we already knew the value of v from our calculation for rows earlier on. Solving these equations to find p and q. Now one of these values will always be 0. That is because one of the strategies will never be played by Colin. That is the line that will not have been used in the point of intersection if we had used the graphical method from when we were working out Rose's mixed strategy. So we can see here that we've got p equals 0, q equals 5/7. So in other words, Colin will never play option 1, we'll play option 2, 5/7 at the time, and we'll play option 3, 2/7 at the time. And because the value of the game is 3/7, Colin can expect to lose on average 3/7 every game. So for each of these two now, I'd like to pause the slide and work out the mixed strategy for player B using the value of each of these games. You've got two ways this could be done. One way is to assign probability P to strategy 1, Q to strategy 2, and 1 minus P minus Q to strategy 3 for player B, and calculate it as in the previous example. The other way is to first of all find the optimum mixed strategy for player A and determine which of these 3 options will not be used, so which line will not be intersected in the calculation. So one of the probabilities for B will equal 0. So if you've done this using P and Q as your probabilities, this is the equation you should end up with. Substituting in V equals 1/2 there. And then the equation for if A were to choose option 3 gives us this equation here. So this leads us to B playing option 1 with probability 7/8, option 2 with probability 0, so never playing option 2, and option 3 with probability 1/8. And then similarly for the second game, the equation you'll be led to is here. That is for A playing option 2. For A playing option 3, you'll be led to this equation here, leading us to B playing option 1 with probability 1/3, never playing option 2, and playing option 3 with probability 2/3. Now complete exercise 6.3 on page 100.